This lecture is recorded because Professor Ildu Kim last minute had to cancel his trip. But let me introduce you. Afterwards, there will be a possibility of Q&A. He will remotely connect with us. Professor Ildu Kim is the chair professor of Department of Material Science and Engineering at KAIST and director of the Membrane Innovation Center in this institute. He received a PhD degree from KAIST. He was a postdoc at MIT, and Professor Ildu Kim Research Group is dedicated to developing novel method of synthesizing various organic, inorganic nanofiber materials that are optimized for use in ultra-sensitive chemical sensors, including those used for detection of environmental gases, hazardous gases, and brief gases analysis to diagnose disease. Professor Kim has published over almost 400 papers, 62 cover feature papers, 5 book chapters, and holds 240 international patents. He, of course, received numerous prestigious awards, and he is also the fellow of Korean Academy of Science and Technology. So let's play Professor Kim lecture.
Hello everyone, good morning. Thanks for kind introduction. It's my great pleasure and honor to present a plenary lecture at 8th International Conference on Electrospinning. Unfortunately, due to very important project presentation, I couldn't join you. Please excuse me. First of all, I would like to thank Ulla for kind invitation, as well as preparing such a wonderful event for all of us. You did a great job. Congratulations. Today I'm going to introduce our very recent activity on the nanocatalyst design, especially have a high mechanical stability and high thermal stability. Before introduction of today's talk, I would like to introduce our lab activity. So our lab name is Advanced Nanomaterials and Energy Lab, and we are exploring various nanomaterials synthesis, zero-dimensional particle, high-entropy alloy particle, and single-atom catalyst, and which are decorated on the one-dimensional carbon nanofibers and two-dimensional oxide, the nanosheet structures. Then we apply these materials for chemical gas sense application with high sensitivity and selectivity, and energy storage, energy generation application, including the catalysis application. Within recent 3 years, we have published more than 24 cover article, and today I'm going to mainly discuss on this 4 article, how we can design such a thermally stable and mechanically stable the nanocatalyst on the one-dimensional the nanofiber structure. Let me show you 2 examples. The first example of the metal organic framework. The MUF is consists of the metal node and organic linker. And you can see this is a conducting MUF. It has high porosity and high surface area. So we can simply infiltrate the metal ion into the inner cavity, followed by the simple reduction process. We can synthesize small catalytic nanoparticle. It looks like the bulb structure, socketed structures. For example, platinum particle and palladium nanoparticle. And also, once we introduce 2 precursors at the same time, then we can create a bimetallic nanoparticle. We further explore this technique, combining by the microfluidic solution sharing printing technique. So you can see here 3 channels. The first channel is copper ion injection, and second channel is organic linker injection, and last one is platinum ion injection. After these three precursors are injection. They are mixed together and spread it on the sensor substrate. Then also we incorporate this sodium borohydride for the reduction of this platinum ion. Then, surprisingly, we could see the creation of this platinum nanoparticle within this 100 nanometer thick, ultra thin, the MOF thin film layers. Unfortunately, this MOF is not stable at high temperature. That's why we need to develop the oxide catalyst and also carbon support structure for high temperature operation. So most case, this small particle decorated on oxide support layer, when we increase the annealing temperature, they are always aggregated and eventually detached from these oxide support layers. On the other hand, this exsolution starting from the doping. So you can see this is the perovskite structure. B side doped the element, reducing atmosphere high temperature annealing. This dopant, the element, is extruded, then segregated on this oxide support layer, forming this extruded catalyst structures. The main beauty, the main advantage of this exsolution, then you can see socketed structure. So that's why we can see high mechanical, high thermal stability when we use this exsolution catalyst particle. This exsolution behavior is well observed in perovskite structure, and you can see here socketed structure, and also even binary oxide, we also see this exsolution behavior. However, this exsolution need high temperature operation, reducing atmosphere annealing, so lamping and curation and cooling. So it takes time. So that's why our team, we are interested in the low temperature exsolution. So we developed the 2D oxide nanosheet. So this is iridium doped tungsten oxide nanosheet. Then tungsten oxide undergo the phase transformation at high temperature. So when we use this iridium doped tungsten oxide, we could see the low temperature exsolution, 300 degrees C, 400 degrees C, and 500 degrees C. Then we also ZIF8. So by annealing this ZIF8 in air atmosphere, we can synthesize porous zinc oxide. After incorporation of this foreign element, then additional the reducing atmosphere annealing, and also we can see this exsolution. Single element particle, then also bi-elemental particle, bimetallic particle can be synthesized using this ZIF8 templated zinc oxide material. But temperature is much reduced as compared to the perovskite oxide, 300 and 500 degrees C, but still high temperature. So that's why we interested in this socket-like structure, then combined with the ultra-fast processing step. So today I want to introduce these two approaches. The first one is carbon thermal shock synthesis, and second one is flash thermal shock synthesis. As you can see in this temperature profile, so duration time is just 20 milliseconds, 0.02 second temperature increase up to almost 1,500 degrees C. After then, 20 millisecond duration, then rapid cooling, then we can create high-entropy alloy particle, then single atom catalyst using this carbon thermal shock synthesis and flash thermal shock synthesis. So let me show you several case studies. The first topic is Joule heating, carbon thermal shock synthesis, and second topic is flash thermal shock synthesis using IPL, the intense pulse light. Then after that, I want to show you some our recent progress on a nanofiber membrane synthetic strategy. Then after that, I will summarize today's talk. Alright, so let me start with the carbon thermal shock synthesis. 2018, Professor Liang Bin-hu and also Professor Jury from MIT and Maryland University, they successfully demonstrate the carbon thermal shock synthesis for the synthesis of the high entropy alloy particle. So this is a carbon nanofiber. Then you can see the decoration of a small particle, high entropy alloy particle. So this is the duration time, 60 the millisecond level, and rapid cooling. So after formation of this carbon nanofiber, then coating of mixed precursors and apply the bias and current, temperature increase up to 1500 degrees C. After rapid cooling, there is no time for phase separation. In this case, we can see the creation of the high entropy alloy particle. We also developed our own Joule heating setup. We spent almost 3 years for creation of our own Joule heating setup. Jong-seop Nam, we spent a lot of time, and after the careful integration of this Joule heating setup, also we can control the oxygen partial pressure. We can directly synthesize metal oxide catalyst using this Joule heating. So you can see here temperature increase up to 1500 degrees C by simply applying the voltage and current. This is a long duration, and short duration is also available. Then we can increase the area. 10 centimeter and 10 centimeter carbon thermal shock synthesis is also possible using our own system. Then also we explore, you can see here, this is 2 precursors. Then for the synthesis of platinum palladium particle and 3 elemental particle, 4 elemental particle can be synthesized using this Joule heating setup. Then also by controlling the relative ratio, controlling the stoichiometric ratio, we can synthesize 3 element particles: cobalt, nickel, iron, then cobalt rich, then nickel rich, and iron rich. The element you can see different behavior, right? So different particle size, different composition, and also we can manipulate the catalytic activity using this mixed alloy material. By simply using the Joule heating approach, we can easily synthesize high entropy alloy particle attached on these carbon fibers. However, mild condition is okay, but harsh operation condition, high temperature operation, this particle is easily aggregated, right? Then easily detached from this carbon surface. That's why we need a tightly anchored, socketed structure for long duration, long cycling operation, especially harsh condition. As a case study, we use the nanofiber yarn technique. The last Malaysia electrospinning conference, my colleague, my friend, Professor Andreas Reiner, introduced this yarn spinning technique. We also use this technique for the pen, the nanofiber synthesis. So this is a 260 micrometer thickness. Then individual fibers are entangled. So we expect the high surface area. After the carbonization process, we could synthesize carbon, the nanofiber yarn. So by applying the bias and current, you can see the temperature sharply increase, right? Then after simple the coating of the metal salt, actually this carbon is hydrophobic, so we need the surface treatment. For example, oxygen plasma treatment. After that, this metal salt is easily coated, well coated on these carbon fibers, individual fibers. After Joule heating, then for example, gold precursors, we can see the creation of a high density the gold nanoparticle. Dr. Jae-Hwan Nam successfully demonstrate this work. Then also, not only these carbon fibers, we can simply use, of course, these 10 nanofibers. Then 2019, Professor Andreas Greiner team successfully demonstrate high density, then high strength nanofiber yarn. Then also, we use these 10 nanofibers as support layers, additional coating of ITO, then followed by ZIF-8, the molecular sieving layers. Also, we can use as a gas sensing material for the NO or the hydrogen detection. Okay, so let me introduce synthesis, this rapid Joule heating. So we use the two-step Joule heating. So carbon nanofibers, individual fibers, and we introduce 5 nanometer thick, the titanium oxide. Then we did the Joule heating to synthesize crystallized titanium oxide. Okay. Then ruthenium, rhodium, palladium, iridium, platinum mixed precursors are coated on these carbon nanofibers. Then second step Joule heating. Then surprisingly, these small high-entropy alloy particles are well socketed within these oxide layers. So we counted the 50 particle, average particle size is 2.4 nanometer. High-density particles are well embedded. So you can see ruthenium, rhodium, palladium, iridium, platinum element compositions are well observed. Then without titanium oxide support layers, of course, we could see the formation of a small particle, but certain area is not well decorated. On the other hand, with titanium oxide over layers, you can see high density particles are well formed. We further control the loading amount, so 2 millimole, 20 millimole, 40 millimole. By simply controlling this loading amount of the precursors, you can see the 1.2 nanometer average particle size, 2.4 nanometer, 9.6 nanometer. We can easily manipulate particle size by simply controlling the loading amount. So we successfully demonstrate the CO2, the conversion catalytic activity. So using the reverse water gas shift reaction, actually this reaction is occurred at 600 degrees C, fairly high temperature in terms of the used catalytic nanoparticle, right? 600 particle, this small particle must be merged together, right? So without titanium oxide over layer, just the high entropy alloy, the catalyst decorated carbon nanofibers, CO2 conversion efficiency is low, then just 24 hours operation, then you can see there is no more activity. On the other hand, titanium oxide supported high entropy alloy particle decorated on the CNF, it showed almost 300 hours operation. Even after 300 hours operation, this catalytic particle maintain their original microstructures and morphology. We demonstrate the carbon thermal shock synthesis by introducing the oxide over layer for the formation of the socket-like structure. Let me move on the flash thermal shock. Carbon thermal shock synthesis, we always need carbon fibers. But this flash thermal shock, IPL, using the xenon flash lamp, so remote process. So that's why we can use a broad range of the support material. So I'm going to show you 3 case studies. The first one is oxide material, and second one is graphene oxide, and last one is the carbon nanofibers. How we can design the catalytic particle and single atom catalyst on this material. So 10 years ago, we used xenon flash lamp, IPL, intense pulse light, for the silver nanowire welding. So this is the silver nanowires that we synthesized. Then we covered the graphene on top of this. Then after IPL exposure, the temperature is sharply increased. After then, the silver nanowire contact part forming, they are diffused, then forming junction. These nanofibers, we can see much improved conductivity behavior. So conventional, the furnace annealing, so you can see 5 steps, right? Voltage applied bias, then Joule heating, thermal conduction, thermal equilibrium, then increase in temperature of the sample. On the other hand, the flash thermal shock, the IPL, just exposure, light exposure, is a light irradiation, then generation of the phonon, then photothermal effect, we can see the temperature increase. So I like this Joule heating. Yes, this is a very powerful approach for the millisecond level high-entropy alloy and single-atom catalyst design. But as I mentioned, we always need the carbon material. But this photothermal effect, without carbon material, we can use this IPL process because, as I told you, this is a remote, just a light irradiation approach. And also, we can use the large area, the IPL, the genome flash lamps. For example, this is a 15 centimeter and this is a 7.5 centimeter large area. So we can cover mass production, large area synthesis. For this IPL, so we use the visible light spectrum. So that's why black oxide is okay, right? So low band gap material, we can easily use this IPL processing. However, white oxide band gap is large. For example, tin oxide 3.6 electron volt, zinc oxide 3.4 electron volt, titanium oxide 3.2 electron volt. So it's a little bit challenging. So that's why we need a careful control the materials microstructure selection. We need the low crystalline size and high defect density, a lot of vacancy, then band gap transition, direct to indirect transition, then low thermal conductivity, and highly porous, the nanostructure. In this case, we expect the IPL, genome flash lamp, flash thermal shock synthesis. For example, this is a tin oxide, about 90 the nanometer particle. This is a 44 nanometer particle, and this is 6 the nanometer, the small grain size tin oxide. So in this case, temperature increase, IPL exposure, temperature increase up to 400 degrees C, 400 degrees C. In this case, 1,600, 700 degrees C. So we expect the nanocatalyst synthesis. That's why we use this tin oxide, the nano sheet. After that, we simply drop coated this metal salt, platinum, ruthenium, iridium, the mixed metal salt for the synthesis of ternary oxide. So please take a look at this temperature profile. So just 20 millisecond duration, temperature sharply increased up to 1,700 degrees C and rapidly cooled down. Then you can see platinum ruthenium, platinum iridium, and platinum ruthenium iridium alloy particle is well formed on this oxide support layers. Then, as I mentioned, the sequential, the light exposure is possible for mass production of this 2D oxide sheet. The platinum and platinum ruthenium and platinum ruthenium iridium particle decorated to the oxide sheet. So synthesis processing time is very short, right? 20 milliseconds, less than 1 second, we can synthesize catalytic particle decorated nano sheet. Then we successfully demonstrate the hydrogen sulfide, then also methyl mercaptan sensing sensors for using this technique. Then I mentioned the exsolution. Then I'm curious. We are very curious on this IPL also can induce the low temperature exsolution. Actually, the short time the exsolution process. As I told you, this is 5 500 degrees C, the exsolution, using furnace annealing, and this one is just 0.02 second, the light exposure, then we could see the exsolution behavior. Platinum doped tungsten oxide, rhodium doped tungsten oxide, iridium doped tungsten oxide. After the light exposure, then we can see this particle, platinum particle, and rhodium particle, and iridium, the nanoparticle, is well absorbed on this tin oxide, the nanofiber structures. Without exsolution, before exsolution, just platinum doped tungsten oxide, you can see a relatively low gas sensing property. This is a hydrogen sulfide gas sensors. Then after just one shot light exposure, then you can see dramatic, the increase, the gas response. So using the light, also we can induce exsolution behavior. I'm very proud of this approach because we can dramatically reduce the processing time for this catalyst design. Then I'm going to moving on the other case study, the graphene and nanofibers. So we mixed three materials, graphene oxide, melamine is the N-doping site, then metal ion. We mixed all together after the xenon flash lamp irradiation. Then we can see here temperature increase up to 2,500 degrees C. Then small, very tiny, this single atom. Cobalt single atom, nickel single atom, platinum single atom. When we mix the two precursors at the same time, then cobalt and nickel mixed the single atom catalyst successfully decorated on this reduced graphene oxide. We can apply these materials for gas sensors and as well as hydrogen evolution reaction catalyst. We further explore high-entropy alloy catalyst design. Previously, I mentioned photothermal shock synthesis can induce high-entropy alloy, the catalyst on carbon support, and also the light exposure. So we used the 6.5 centimeter carbon nanofibers and 5-element mixed precursors, then IPL exposure, then platinum, iridium, iron, nickel, cobalt. High-entropy alloy is formed on these carbon nanofibers. Then we further explore the 9-element, okay? This 9-element high-entropy alloy particles are also well formed on these carbon nanofibers. As compared to the previous reference, it takes time, but in our case, 10 milliseconds is enough for synthesis of high-entropy alloy particles. So you can see this is a platinum, iridium, iron, nickel, cobalt, ruthenium, cerium, indium, strontium, high-entropy alloy. Then we simply change the support material, the graphene oxide, and also the MXene. So we could synthesize this 5-element particle. So I emphasize remote process, light exposure, so that's why we can use a broad range of the substrate for this technique. So photothermal annealing, as I mentioned, we first will demonstrate this technique. Then host material, the graphene-based material and carbon nanofiber material, MXene, even metal oxide. White oxide is also possible for the synthesis of a single atom, high-entropy alloy, and also even exsolution or catalytic particle synthesis is available using this IPL, the xenon flash lamp approach. Recently, we further explored the synthesis of nano onion from the nano diamond using this based on this photothermal annealing. We increased temperature up to almost 2,500 degrees C. Surprisingly, this nano diamond converted to the nano onium. Then additionally, we could decorate this single atom on this nano onion. All right, so I'm moving on the nanofiber membrane synthesis. Let me briefly introduce about it. Then I know that you all expert on the electrospinning, so I'm not going to discuss in detail about the processing. Then also our lab, we spend a lot of time for the synthesis of these nanofibers, creation of these nanofibers. So this is a 35 centimeter width roll-to-roll machine, and this is a 1.2 meter width electrospinning machine. And you can see here, this is a multi-nodule system, so it moves left and right. So we can cover the relatively large area. Then we successfully licensed the 13 technology to the various company. So using this electrospinning, we can synthesize polymer material, biodegradable and antibacterial, and antivirus, the nanofibers. Then using aligning technique, that we can achieve the high density align the membrane. This is a collaboration with my former graduate student, Dr. Kiro Yoon, and this is a PTFE, the aligned nanofibers. And also we can align these the oxide fibers by combining the ALD, the aluminum oxide coating, then followed by the high temperature annealing that we can burn out for the nanofibers. Then also we can decorate this the dye, specific dye. For example, this one is a thermochromic dye. So we can see here temperature change, the color changing, right? Then this is hot water, the injection, this black thermochromic dye converted to the white. So we can measure the body temperature using this approach. And now we explore the colorimetric sensors using this technique. Then also regarding to the carbon nanofibers, then we synthesize various carbon nanofibers combined with additional, the second step, material synthesis. For example, electrospinning combined with hydrothermal, the solvothermal synthesis. We can see here formation of a brush-like cobalt nitride catalyst. We use this for the lithium-ion battery application. Then, as I mentioned, now we are focusing on this flexithermal shock synthesis for high-entropy alloy catalyst design. Then also recently we succeeded in a synthesis of aligned carbon nanofibers. As you can see here, thickness is lower, but conductivity is higher. So we can increase the fiber density within the same volume. Then also we can explore metal oxide nanofibers using electrospinning technique that we used polymer nanofiber as a sacrificial template. Then we synthesize this catalyst, the sensitized the nanofiber for sense application. Then recently, the PhD student Jong-won Baek succeeded in non-noble metal decorated nanofibers. This is a cobalt dot seria decorated tin oxide hollow tube structures. Then we could see the high sensitivity, the isoprene sensing behavior using these fibers. Additionally, we're working on the light activated, the room temperature gas sensors. For example, this is indium oxide, okay? Band gap is about 3.0 electron volt. By simply doping the bismuth within this indium oxide lattice, then we can reduce the band gap. That means the blue light, the activation is possible. But green light activation is not enough, so that's why we additionally decorate the gold particle surface plasmonic effect. In this case, this green light activation is hugely increased. So room temperature green light activation means then just this indoor the light, so we can use these sensors for the high sensitivity, high selectivity, the NO2 gas detection. As compared to the other light activated NO2 gas sensors, then you can see low concentration sensing behavior dramatically increased. So recently published, last week, published in Advanced Material and inside cover article. All right, so this is a take-home message: ultra-fast catalyst synthesis, high-entropy alloy catalyst, and single-atom catalyst using carbon thermal shock synthesis and flash thermal shock synthesis. And also we combine this technique with the nanofibers, carbon nanofibers and metal oxide nanofibers for making the socket-like structures, thermally, mechanically stable nano-catalytic design. Okay, so last year I promoted to the executive editor, so the submission of a high impact work is most welcome. And also I'm organizing the KAIST, the Emerging Material Symposium every year. So so far we invited Nobel laureate Professor Andre Klein and Professor Stanley Whittingham, and also many editors join this KAIST symposium. And next Monday and Tuesday, the 18 ACS Nano editors will join KAIST. So your attention, your attending is very welcome. So you can simply check the Google searching, so KAIST Emerging Material Symposium and ACS Nano Summit 2024 at KAIST, so you can simply find the link. So if you cannot find the link, please let me know, then I will invite you. And last year, I was in UC San Diego as a sabbatical year. Then last Sunday, my family returned back to Korea, so I feel a little bit of a jet lag. Then we collaborated with Professor Joseph Wang. So he is the best expert on the nano rocket, the nano motor. So that's why we further extended the electrospinning technique, making the nano rocket. So inside these fibers are decorated by the catalytic particle. Then hopefully the next electrospinning conference, I want to show you some interesting research work on this nano rocket development. So thanks for your attention. Then also I would like to thank all our group members. And this is the last Malaysia conference image. Then also at the end of my presentation, I always show this zebra. So they helping each other, they are collaborating each other. So I want to collaborate with Ula and also all of you. Thank you very much.
So now we try to connect with Professor Il-do Kim online.
Hi, Ula.
Hi, good morning. Good morning. So,
see you.
We can open now the Q&A session. So if you have any questions. Sure. Yeah, great.
Hello, Professor. Thank you for this nice presentation. My question is that how can you induce selectivity for gas sensing by membrane? Because it's a real challenge to do the selectivity by changing the metal nanoparticles or by changing the aromatic moiety in the membranes.
Okay, so thanks for the interesting question. So actually, the in gas sense application, selectivity is always an issue. So we know certain catalytic particle can provide specific binding with a specific target. Yes. So we can provide a certain degree of selectivity. Then also we can incorporate the metal organic framework. So for example, here, so in this case, this one is a ZIP-8. So ZIP-8, the pore size is 0.32 nanometer, and hydrogen is, the kinetic diameter is 0.289 nanometer, smaller than the pore size. In this case, we can also provide certain degree of selectivity. So we can use molecular sieving layer, and also we can incorporate the catalytic particle. Then also we can use the machine learning approach, so making the 3-4 the gas sensor array, and we can see also using the PCA, the principal component analysis, we can also get certain degree of selectivity. But I know this is a quite challenging approach. Thank you.
Yeah, there's more question. Daniel, over there.
Thank you. Very nice presentation. Thank you very much. My question is about how far can you go with the production of carbon nanofibers with your processes that you showed today?
Regarding to the carbon nanofiber synthesis, actually, we mainly working on the small, the single nozzle system. Then also in Korea, one of a company making the large area, like the 1 meter, then also the roll to roll, the sequential, the sintering, the reducing atmosphere sintering, so they provide 1 meter and also large area, the carbon nanofiber synthesis. But in the lab scale, the university scale, the large area, the carbon nanofiber synthesis is challenging because due to the limited furnace size. So in our case, we can synthesize A4 size, the carbon nanofibers. Thank you.
Any more questions? Cannot see any. So thank you so much, the speaker, and connecting with us far away.
Thank you very much. I hope you enjoy the electrospinning conference, and I hope to meet you the 9th electrospinning conference in person. Thank you very much.
Thank you so much.